Okay, welcome to Thinking Beyond. It is our last webinar of the semester, so I don't have any announcements except to say that we will continue on next semester at the same day and time, the last Monday of the month at 6 p.m. Mountain Standard. So look out for announcements mid-August for registration. And if you have any questions during tonight's presentation, just use the Q&A feature at the bottom of your screen and you can ask them and we will get to those at the end of the hour. And that's all I have. So I will go ahead and turn it over to Paul Davies, the Beyond Center Director and moderator for tonight.
Thank you, Jessica, and hello to everybody and welcome. So it's my pleasure today to introduce a very distinguished Australian physicist, Howard Wiseman. He began his career at the University of Queensland, and then he spent time in New Zealand at the University of Auckland before returning to Queensland, most recently at Griffith University, where until last year he was director for the Centre for Quantum Dynamics. And I've always thought of him as a quantum mechanician and somebody at the forefront of quantum information science and things like entanglement and quantum computing. But today he is going to talk to us about a somewhat different subject, the nature of consciousness. But as I'm sure we will discover, these topics interweave each other. And so I'm very much looking forward to hearing what Howard has to say. So without further ado, I will hand over to him.
Thank you very much, Paul, and thank you for the invitation to present to this group, which sure has lots of. I saw some of the earlier talks that you had heard, and yeah, they all sound like very interesting topics. So hopefully this will fit in. So yes, as Paul implied, I am a quantum physicist, and actually, so most of this talk will be very much grounded on quantum physics, but I want to explain why I think that this may tell us something interesting about consciousness towards the end. So my title is Turing, Wigner, Bell: What thought experiments with quantum computers can tell us about thoughts. So yes, I'm at Griffith University, which is in Southeast Queensland here. And the work I'm talking about, so I have various co-authors on papers, but I'll just mention that as I go through. But it's supported by the Australian Research Council and has been by the Blauman Foundation in, I think, Austria or Germany. I probably should know. Probably Austria. Okay, so this is, whoops, is that, there we go. This is an outline of what I'm going to cover. So there are going to be a lot of words and no equations, or almost no equations. So hopefully that's a suitable thing. But yes, so we will have heavy on concepts, but light on maths. I'm going to begin with a very brief, I'm calling it a cartoon history, as we'll see, of quantum foundations from the birth of modern quantum theory 100 years ago up till the 1960s, which is where Wigner and Bell enter the picture. Then I want to concentrate for a while on Bell experiments and more precisely what they actually tell us. Then move on to a more recent field called extended Wigner-Friend theorems. And at that point, I will introduce Turing briefly to lead on to what I'm calling the thoughtful local friendliness theorem, which is where specifically we can see that maybe this is telling us something about consciousness. And then section 5 will be talking about that in some more detail. Okay, so so each section I'm going to illustrate with a picture. So here's my picture for which was actually done for one of the popular articles on the work that we did. So I quite like this one. But anyway, yeah, so a cartoon history of the field to 1964. So I'm going to jump straight in with, I'm going to hope that everybody roughly knows what the standard quantum theory said, as Heisenberg and Bohr in particular uh, formulated it in what was called the Copenhagen interpretation, and jumped straight into Einstein's criticisms of that. So Einstein's criticisms lasted from basically as soon as that theory had been, or that interpretation had been presented, all the way up to, well, his last writings on the topic. So more than 20 years. There's some famous contributions. I'm going to basically mash all of those things together. Okay, it's a cartoon history, not a rigorous history. Anyway, so here we have Einstein and Bohr having a conversation, and Einstein says, "I just can't accept this Copenhagen interpretation, Bohr." So clearly, I'm using Comic Sans font for things which are not genuine quotes of Einstein or Bohr or anybody else. Anyway, Bohr, why not Einstein? Right. And here's the long response. So here we'll see, so I'm using a different fonts for words that are actually words of Einstein, as we'll get through. But anyway, but the cartoon version. Why is Einstein unhappy with the Copenhagen interpretation? So first, he's saying a physical theory should not give a special role to measurement, as Copenhagen interpretation does. What even counts as a measurement? Will a sidelong glance by a mouse suffice to collapse the quantum state? That genuine quote, obviously. Second point, your theory has non-locality built into it, a spooky action at a distance. So when two particles are entangled, one of the parties, Alice's choice of measurement affects what type of state Bob's systems collapses into, no matter how far away he is. This, I think, contradicts the postulates of relativity, which obviously were very dear to Einstein. And then he concludes, a more complete theory with hidden variables defining physical quantities before measurement is the only way to fix the above problems. That was his, as I understand it, his opinion. Now, Bohr didn't agree. Bohr was basically thought quantum mechanics was fine. We should just listen to what the theory says to understand nature rather than coming with preconceptions about nature and criticizing the theory. And most physicists agreed with Bohr, certainly at that time, but there were some dissenting voices. And so in 1961, for example, Eugene Wigner published an essay. I can't remember the title, but it's something like it was on the mind. Um, And here, the way I phrase it is he's saying, I think that Einstein's first problem, his problem with measurement, is a genuine problem. And so these days we call that the quantum measurement problem. And so Wigner went on and says, think about, and this is now a quote, think about the situation if one does not make an observation oneself, but lets one's friend carry it out. Then one could only attribute an entangled state to the joint system of friend plus object, that is, treating them both as physical systems. And he says, this appears absurd because it implies that my friend was in a state of suspended animation before he told me what he saw, and I collapsed his state. And so this is the entry into literature of Wigner's friend, which will come up a lot later. So he goes on, it follows that quantum mechanics cannot be universal theory if it is accepted that my friend has the same types of impressions and sensations as I. Important ideas that we'll come back to later. All right, so that was one important development in the 1960s with Wigner introducing this idea. But of course, a even more important contribution in quantum foundations in the 60s was from John Bell. So John Bell also was not content with the Copenhagen interpretation. He was thinking about Einstein's criticisms of it. In particular, the idea that we could get rid of the non-locality by introducing hidden variables. But then he ended up proving Einstein wrong in that aspect. So here's Bell saying, I've proven a theorem showing Einstein's second reason for wanting to add hidden variables, so to quantum mechanics, so not the measurement problem, but the second reason about non-locality, failed. The reason is not a justifiable reason because adding hidden variables to quantum mechanics cannot remove the spooky action of the distance that Einstein objected to. Specifically, he's saying, quantum mechanics predicts correlations between measurement results on distant entangled particles that cannot be explained without faster than light causal influence. Even though, very important to make, that those causal influences don't allow faster than light signaling. And Bell's attitude to this, or at least it became clear uh, uh, in the following years, was that this was a very strange prediction, that the correlations predicted by quantum mechanics not being explicable without faster than light causal influence was a very strange way for the world to be, and that we should do experiments to test it. And so that leads us on to part two, Bell experiments, and as we'll see, being more precise about what they mean. So let's start with the experiments. So as most of you probably know, these were famously awarded a large part of the award of a Nobel Prize in 2022 for these three gentlemen. And so in chronological order, starting with John Clauser, he's saying this is how the theory of the experiment went. In 1969, I helped develop the theory which made Bell's ideas truly testable. And then in 1973, I performed the first Bell experiments using photons. Alain Aspect saying, I closed a loophole. So that's a potential criticism of the experiment by including fast switching of the settings while the photons were in flight in 1982. And then Anton Zeilinger, I made further advances in theory and experiment, culminating in the 2015 loophole-free experiments. So that's why I date the history of the experiments like that. And so the upshot of that is that the experiments verified that the predictions of quantum mechanics in these situations were correct. And so then the question is, what does that tell us about the world precisely? And so, yeah, so here I'm going to give a better statement, better than the cartoon version, which I very briefly gave before, of what Bell experiments prove. But I think that the statement I'm going to give you is better because it's my own. So this comes from, based on, it's not precisely following, but I've tried to make it a little bit simpler here. This presentation by myself and my colleague, Eric Cavalcanti, who will come up quite a lot in this talk, in a volume published in 2017. Okay, so this is what we say Bell experiments prove. Bell experiments show that the following list of propositions about the world cannot all be true. So at least one of these must be false, in other words. So we have propositions that together make some prediction about what we would see in experiments. And we'll see, though, none of these propositions mention quantum mechanics. So it's nothing about quantum mechanics. These are just very general propositions about the world. Nevertheless, I shouldn't say that they make predictions about what we will see in the experiments. They make predictions about what we will not see in the experiments. In other words, they put constraints on what might be seen. And then we do Bell experiments and we violate those constraints. Okay. And that tells us that at least one of these propositions must be false. Okay. So these are as I said, this is a fairly heavy conceptual slide. So I'm happy. I mean, I wouldn't be surprised if people have questions about this. But I'm going to spend a little bit of time going through that, even though this is not the main topic of the talk. Okay, so we identified four propositions, or sometimes assumptions they're called. Um, so the first is commonly called something like free choice, but this is the version we've got is a causal version of that. And it says this, in a randomized experiment, so in other words, a properly conducted experiment, a choice of setting is uncorrelated with experimental variables unless it is a cause of those variables, right? You don't get correlations for no reason between experimental variables and the choice of settings. Second one, relativistic causality. An event can be a cause only of events that are in its future light cone. Or to put it more colloquially, causal influences cannot exceed light speed. And I should say, so I'm underlining the word cause here. You might be wondering, don't you have to give a definition of the word cause? Isn't this a problematic word? You know, do we know exactly what a cause is? The point is that these assumptions or propositions work together to have empirical consequences, to put constraints on things, even without giving a precise definition of the word cause, just because the way they work together. Okay, so that's the first two. The third one is one that's not often or often not mentioned in discussions of Bell's theorems, but there's an important reason it's here. So this is one we call absoluteness of outcomes. And what that means is the outcome of a measurement is absolutely real. Or maybe I should emphasize that absolutely real. Okay, so not real in a qualified sense, not real only in this world, or not real only for me, just real in the sense that we normally mean the word. Okay, that I don't have to qualify it; it just exists. Now, it's important to note that this is nothing. Whoops, I jumped ahead. All right, so this absoluteness of outcomes is nothing about what causes outcomes or about variables being carried in photons or anything like that. It's just talking about when I have an outcome, that outcome is a real thing, a real single thing. I don't have to qualify it in any way. And this is, yes, so this is important to actually be able to say that at least one of these things must be false. Without that assumption, we can't actually derive, we can't rule out any of the others without this stuff. And finally, what I'm here calling causal explanation. And so this is critical to understanding why I think my cartoon version of Bell saying that there is no explanation of the correlations without faster than light influences, that was his opinion, because the word explanation actually is doing something there. It means explanation in this causal sense, that essentially it's saying that correlations require causation, right? But precisely, it says that if two variables are correlated, then either one causes the other, right? Either way around, or they have a common cause that explains the correlation, right? And to say that it explains the correlation means that I could condition on the value of the common cause, and then that would remove the correlation. I would know then what was causing the correlation. So in any particular instance, I would no longer have that correlation. Okay, so those are the assumptions. As we put it, or propositions that can be ruled out. Yeah, so maybe a point to make is that there is no way we can rule out any one of these individually, right? These propositions. There's no experiment which we can do which would tell us for any one of these whether it's true or false. But if we put four of them together, as here, that has consequences which we can actually test and in fact disprove, meaning that at least one of them must be false. Okay, but which one, right? Which one should we give up? Well, let's ask the characters we've met already. What would obviously this all happened after Bohr died, so we can ask the ghost of Niels Bohr, what should we give up? And I think he would, if he understood what the question was about, he would say we should give up causal explanation. That's the last assumption. This is in line with what I've said all along. The theory is only about the results of experiments, not where they came from. We can say nothing about the atoms themselves. Okay, that last bit is the quote. Um, as for the ghost of Einstein, I think he just wouldn't know. So he's saying, I don't know. All of these propositions seem necessary to me to make sense of the world. Who knows what if Einstein would say anything beyond that? But I think there's definitely nothing obvious that he would want to give up. Okay, so that's Bell's theorem. On to the next topic of extended Wigner-Friends theorems. So you could be forgiven for not knowing what an extended Wigner-Friend theorem is, but they have been a recent topic of quite a lot of interest. And so 3 papers in the field were awarded the Paul Davies Foundations or Quantum Foundations Prize in 2023. So then that's the phrase they used, extended Wigner-Friends theorem. And so these 3 papers, I'll say a little bit more about them next. So the first one, the author was Czeslaw Bruckner. Second one, Daniela Frachiger and Renato Renner. This is probably the most famous of the 3. And the third one is one that I was involved in, as well as Eric Cavalcanti. And that was published that's the most recent of them, published in 2020. So what was in these papers? So based on earlier published papers, I think it's fair to say that Czeslaw Bruckner is the person who had the original idea of extended Wigner-Friend scenarios, which is the idea is to incorporate Wigner's friends into a Bell experiment. But his paper, was really ended up making the same assumptions as Bell. So in the end, it didn't actually prove a stronger theorem or anything like that, but it did introduce the idea. Frachiger and Renner used very different assumptions. And so they proved a no-go theorem, which was rather different in style from Bell's theorem. It was a no-go theorem really about epistemology in quantum mechanics. And yeah, so it was about observers reasoning about other observers and leading to a contradiction. And yeah, so the title, Quantum Theory Cannot Consistently Describe the Use of Itself, but it's not really about doing experiments. Whereas the theorem that we came up with, which in the title is just called a strong no-go theorem, was inspired by Bruckner's work, and so it's along the lines of Bell's theorem, but so it's a theorem about ontology as opposed to epistemology. It's about the way the world is, not about how we reason about the world. And like Bell's theorem, it suggests experiments. And in fact, the reason there are so many authors on this paper is that we actually did a proof of principle sort of toy experiment in this paper. Okay, so I haven't really explained much about what these papers, why is this an interesting thing, or what's special about these papers? How does the Wigner-Friend work? So a key assumption in all 3 of them is that, contrary to what Wigner thought, a friend can be in superposition, so a suspended animation, as Wigner said, when they've made a measurement, but I haven't looked at them. So in other words, that a friend does not collapse the wave function. And even stronger, an assumption that the observation that the friend has made can be reversed by a sufficiently powerful, Wigner or me or Alice, somebody outside the friend. asterisk there because only our paper actually phrased it in terms of reversal, but I think that's by far the clearest way to think about what the assumption means. So for me personally, this assumption needs to be an actual assumption about an experiment we can imagine doing, not just a philosophical thought experiment. So that I want to think about some sort of real experiment. That you might be thinking at this point, well, but I don't believe that. I don't believe that a friend's observation can be reversed. That's, you know, that's not correct. And that's fine. You can think that. The point I want to stress is that for a no-go theorem, it's not necessary for all the assumptions to be correct. In fact, we know that at least one assumption must be wrong because that's what a no-go theorem means. So if I'm going to give assumptions, naturally there are going to be some people in the audience who think, that assumption is wrong, and that's perfectly fine because if you're rational, you have to accept that one of the assumptions is wrong, and if you or know, already what that is, then that's fine. But the important thing then is not for all the assumptions to be correct. That's impossible. The important thing is for the assumptions not to be silly, I would say. And I think good evidence for an assumption not to be silly is actually that it's a view that is widely held, again, not saying universally held, but widely held amongst well-informed people. And also, of course, we want those assumptions to fit together to make a theorem that is interesting and I'd say ideally productive in the sense that it can teach us something new about the world or make us do new experiments or something like that. Okay, and that's what I would claim we do have with the experiment, that the particular version of the theorem that I'm going to explain to you. And just before getting to that, then I want to push Turing into the picture. Why is Turing appearing here? Because I want to think about a real experiment where a friend's observation can be reversed. Okay, and so that makes us think about what sort of friend that could be. And so this is why, yeah, I want to talk briefly about Turing. So so Turing, a little bit earlier than Wigner and Bell, in 1950 wrote this famous paper. So this is the paper which introduced the idea of the Turing's test. And yeah, the bit that I want to read out is this little bit here. I propose to consider the question, can machines think? This should begin with definitions of the meaning of the terms, blah, blah, blah. And he goes on and on and on. And then returning to the original questions, can machines think? I believe to be too meaningless to disturb discussion. So basically saying we can't actually give rigorous definitions of these things. Nevertheless, I believe that at the end of the century, the use of words and general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. And so I think Turing was not quite right like it was not the case at the end of the 20th century, that everybody was just talking about machines thinking. But I think it's a pretty good bet to say that by the end of this century, that will be the case. Okay, so I think maybe his timing is off, but his instinct was correct. Okay. So then this is what the background we need so I can explain what I call the thoughtful local friendliness theorem. And so this is exactly what we called it in this paper. So this with Eric and another colleague, Eleanor Riefel. So this is not Eleanor in the picture. So she does work with quantum computers, but this is just I actually couldn't get a random person looking at an IBM quantum computer processor, just because that was the picture I could find. Okay, so, but it gives you a hint. Yes, so this is a picture of my creation to give you a hint of what the thoughtful local friendliness looks like if you hadn't already guessed from the fact that I put Turing up just in the previous slide. Okay, so to explain this new theorem, I want to go back to Bell experiments. All right, so that this is exactly the slide I had. Oh, it's not exactly this slide. Almost exactly this slide. I just want to introduce one. So here I've actually introduced a word, metaphysical propositions. So I said before that these are propositions that cannot be individually tested, but they can be tested together. And this is why these are called metaphysical propositions rather than physical propositions. So a physical proposition, a physical theory, you usually expect that's something that can be tested. So these things cannot be tested. Nevertheless, the surprising thing that Bell showed is you put appropriate list of metaphysical propositions together and you can actually disprove them. All right, so just to remind you, the four propositions are free choice, relativistic causality, absoluteness of outcomes, and causal explanation. Right. So that, and Bell experiments show that those one of those must be false. So I want to, for reasons will become apparent, distinguish that from Bell's theorem. So Bell's theorem says that those four metaphysical propositions and a proposition which is not metaphysical, an empirical proposition that the predictions of quantum mechanics are accurate, they together make a contradiction, right? So Bell's theorem in 1964, the experiments had not been done. So the theorem is about, right, these metaphysical propositions and this empirical proposition lead to a contradiction. All right, so that's actually what Bell's theorem says. So in a sense, you could say we don't need Bell's theorem anymore because we've got the experiments, right? I mean, obviously it's still Bell's theorem, but we don't need to state it this way. However, there are some versions of Bell's theorem where we haven't yet done the experiment, and in more of a more interesting version, a stronger version. What do I mean by a stronger version? I mean one which makes use of metaphysically weaker propositions. So specifically, what I've done going from the previous slide is change absoluteness of outcomes into absoluteness of observations. So you might be skeptical about whether, detector clicks are really, they are absolutely real, but hesitate to say that an observation made by a human being is not absolutely real, right? Because we have a preference, we have our internal uh, experience, which makes us tend to think that observations by human beings are absolutely real. So why is this experiment not being done? Because humans are very slow at making observations. It takes us about a second, probably, or at least a good fraction of a second. So to do an experiment like this, where you can rule out relativistic causality, you would have to put the two people involved in the experiment roughly a light second away, which would mean one would have to be on the moon or something like that. So this is definitely a doable experiment, but probably not for a decade or two. Okay, and I think it would be an interesting experiment to do. But at the moment, all we can say is that this is a theorem that if the predictions of quantum mechanics still hold true when we do the experiment that way, then we can rule these things out. Okay, so this is just a way station. We're almost at the actual local friendliness theorem, and we'll see why I wanted to do it this way. But you could really, like, if someone was proposing to the, US government or the Chinese government or someone to do this experiment when there's a moon base, um, somebody else might object to say, why would we bother doing the experiment? We already know what's the wrong assumption here, right? Bohr told us what the wrong assumption was, and surely any reasonable person would agree with Bohr that the wrong assumption here is this causal explanation that if two variables are correlated, then either one causes the other or they have a common cause. So that's the same assumption that should be given up, whether it was, Bell experiments we've already done or these new types of Bell experiments. So why bother spending all that money to do a theoretically stronger Bell experiment. And this is then my motivation for saying, let's look at the local friendliness theorem. The point of it is that we don't use this assumption of causal explanation. That assumption is just not part of the theorem, and that's why it's interesting. Okay, so the 2023 thoughtful version of the local friendliness theorem. I should have said that in the 2020 paper we introduced the term local friendliness theorem, but yeah, the 2023 paper we distinguished by thoughtful. So it shows that the following list of metaphysical and I'm going to say technological rather than just empirical this time, as we'll see, propositions about the world cannot all be true. So the same free choice, the same as before, relativistic causality, the same as before, absoluteness of observations, the same as just I had before, an observation made by a human being is absolutely real. But no causal explanation. We don't need that assumption, but we do, however, have a new assumption, which I'm calling here friendliness, which says if an artificial intelligence displays human level abilities, their thoughts are as real as a human being's. Okay, so obviously it's a completely different type of assumption from causal explanation. So we're not just replacing that assumption with a similar one. It's a completely different type, but nevertheless, we can get a contradiction now with these four and these technological assumptions or propositions that human level artificial intelligence is possible and that large scale and fast quantum computation and communication is possible. Right, so how is that going to work? I want to introduce you to my friend Kwali, or Alice's friend here. So in the Bell experiment, we just have two parties, Alice and Bob, but now Alice has a friend. And Kwali is a huge quantum computer running a human-level artificial intelligence algorithm, which we've assumed to exist by the theorem. Before starting, then, Kwali must pass an open-ended Turing test so that we are going to be convinced that he really is a human-level artificial intelligence algorithm. And then we can get into the experiment. So the first thing that, to note is that Kwali for this to be a proper experiment, Kwali must be treated as a party in the experiment, not a system. So, for example, that means that Alice can't know Kwali's private thoughts, and she doesn't need to for the experiment. Also, he must agree to partake in this experiment beforehand. And you might wonder, well, why wouldn't he agree? Why might he hesitate? Well, because in each run of the experiment, Kwali is going to have to be isolated for roughly 1 second of time. And in some runs, his memory of that run would be completely wiped. So you'd have no memory of that run. So he'd have to be comfortable with that type of experiment in order to do it. Okay, what's he actually going to do in the experiment? He's going to observe a qubit. Now, a critical thing is, so a qubit is just the smallest possible quantum system, for those who don't know, with two possible states. That mean when we say observe a qubit, not in the sense that he puts it into a detector and then looks at the bit that comes out of the detector. No, he's a quantum computer, or he's running on a quantum computer. He can directly take in a qubit as an input, a quantum input, and process it, right? According to the artificial intelligence algorithm that processes any input. Okay. And so in particular, he's going to think about what the qubit is, what the result of the state of the qubit is. And we're going to use the letter C, because originally it was Charlie, to represent his thoughts about what he saw. Yeah. If they exist, we'll see in a minute. Okay. So here's Kwali in context. So Kwali, sees something, writes a message telling Alice what he saw, which gets sent out to Alice here. Now then Alice has a choice. She can either open the envelope and read what Kwali saw or what message he sent, or if her random number generator is not x equal 1, but x equals something else, x equals 2, say, then she does a very different thing. She takes this envelope unopened, returns it with its quantum message, right, back to Quali, and then presses a button which ensures that the quantum computer on which Quali is running runs in a logical reversal all the way back to the time before Quali had interacted with the qubit, which is this Q1 qubit here. And then at that point, Alice just says, ask Quali, oh, can you just send that qubit on to me? And he has no memory, presumably, of having ever interacted with that qubit. So he thinks nothing of this. He says, okay, yep, sure, pass it on. And so in that case, Alice gets the qubit Q1 and makes her own measurement on it in some other basis, measures a different property of it. And you might know there's also Bob over on this side, as in a normal Bell experiment, and he has his own qubit, Q2, which he's also measuring in his own basis and getting his result B. Our result A is then either what she gets from measuring the qubit directly in some runs, or in other runs, just whatever Quali told her. Okay. And in space-time, these things have to be separated out. So I think I won't go through this in detail. This is meant to be a space-time diagram. But yeah, these things have to be spread out in a way that we can make use of the relativistic causality assumption. So yes, I said Bob's doing his own thing over here, with his own free choice. So the critical thing is that these thoughts of Quali exist absolutely and independent of Alice's choices or Bob's choices, independent of X or Y, right? If we make regardless of whether Alice just gets what Quali sent or she does this complicated thing of reversing and getting the qubit and making her own measurement, right? In either of those cases, the thought of Quali exists absolutely if we make these assumptions in the theorem, right? The assumptions of free choice, relativistic causality, absoluteness of observation, and friendliness towards Quali. And that's what does all the work for it. The fact that this C really exists lets us, lets us derive some consequences. Okay, so just to say that, as I said, for me, it's important that this be a real experiment, but it's not going to be an experiment that happens in my lifetime, I think, because we estimate how difficult it would be, how big the quantum computer would have to be, how fast it would have to be. And yeah, these are benchmarks a long way off. We also, as I said, we need to put the different parties a long way away. But if we can do all of that, and I don't think this is an impossible experiment, we can imagine in 100 years' time, maybe even 50 years' time, this might be possible to do. And if we do that experiment, we can gather statistics, right? The probability of Alice and Bob's outcomes given their settings. We can absolutely get that from repeating the experiment many times. But the point is that the four metaphysical assumptions, which imply that, as I said, that C, Quali's thoughts, exist independent of X and Y, plus the fact that when Alice is random number generator is X equals 1, she just asks, or she just opens the envelope and writes down whatever Quali had sent her. That leads to constraints, which we call local friendliness constraints on this probability distribution. And then the punchline is that if everything works as expected, the quantum computer, the quantum communication, right, then what we would measure empirically for this probability distribution will violate the constraints of local friendliness, and therefore one of the assumptions must be wrong. Okay, so then that again asks the question, well, what should we give up? And so a new commandment I give unto you, you've all got to work things out for yourselves. Okay, so I'm not going to tell you the answer to this. A lot of people work on these theorems and say, and this is the conclusion you should draw from the theorem. I'm not going to do that, but I will give you my own. I'll give you my own thoughts at the end. All right. So to remind you what the theorem is that the following list of metaphysical and technological propositions about the world cannot all be true. Free choice, relativistic causality, absoluteness of observation, friendliness, and then these technological assumptions. So every one of these can be questioned, and for every one of these, I can find someone who will uh, give a reason, reject that. But let's start with the ghost of Bohr again. But so he now no longer can reject uh, causal explanation. So he's saying, gee, now I don't know, since giving up causal explanation is no longer an option, but I'd probably give up friendliness, number four. That is, I probably accept that my, whoops, typo, that my AI friends may not cohabit the classical realm with me. Okay, so Einstein's not worth asking because he was already confused about Bell's theorem, but we can ask Bell, and I think everybody knows what Bell, well, I know what Bell would say. He'd say, I've always been inclined to give up assumption two, relativistic causality. In other words, to accept that there really are faster than light causal influences. So that's two, but we can keep going. So here's probably a face familiar to many people, Sabine Hossenfelder. She would say, give up one, free choice. This is also my solutions to Bell's theorem. And another face over here, Chris Fuchs. I, he's saying, it is fundamental to the philosophy of cubism that that I give up assumption three, absoluteness of observation. That's just a little dig. That is also my solution to Bell's theorem. And he explains a bit more. What I observe is real to me. What you observe may be real to you, but it is not real to me until I find out about it. And this is the same whether you are a human or an AI running on a quantum computer. Okay. Okay, so that covers the four metaphysical assumptions, but there are also interesting things to say about the technological assumptions. So here's Sir Roger Penrose, who has interesting ideas. I think for my theorem, or our theorem, what he should say is, I do not believe that human level artificial intelligence is possible on a digital computer, despite current chatbots. Human level intelligence arises from an undiscovered process, uncomputable, irreversible, quantum, and general relativity related inorganic brains. So that's a specific, he would actually reject that assumption that it's actually impossible to have human level artificial intelligence on a digital computer. But a different type of technological assumption would be questioned by David Chalmers. So he's done some recent work where suggesting that if we implement a sufficiently sophisticated AI in a quantum computer, we may find it impossible to put in a superposition of different thought processes because of wave function collapse. And if that's the case, then universal quantum computing is empirically false. There are some things that we should be able to do with a quantum computer which we just can't. So that's a technological assumption that would be false. Okay. What do I think? And since everybody else gets to be represented by a younger version of themselves, I thought, why shouldn't I as well? What do I think? So as a scientist, I'd like what Chalmers is suggesting to be true. I'd like universal quantum computing to be impossible because conscious states cannot be superposed. Why would I like that is because that would be the most important scientific discovery since Newton, I think. I think it's very unlikely, but I think it also does need to be tested. All right. But so that's as a scientist. As a human, I would be happiest if Penrose were right. That human level artificial intelligence on a digital computer be impossible. But I also think that's very unlikely. So given if we ignore the things that are very unlikely, what do I think? So metaphysically then, I would be inclined to give up friendliness to AI on a digital computer. And why is that? So I don't think that biology or some digital, non-digital process is necessary for passing the Turing test. So not like Penrose. I think it's perfectly plausible that we will have digital computers that can pass the Turing test, exhibit human level artificial intelligence, in other words. However, I think that some non-digital process may be necessary for there to be any experience of the thoughts of those computers, for any sentience or feeling to exist. And I would say that without that, without the actual experience of thoughts, that is not, yeah, that an AI's thoughts are not as real as a human being's. So that I wouldn't, that's why I would reject friendliness and to say that there's just nothing there. Right? They can pass the Turing test, but that doesn't mean that there is an actual thought existing and in their minds. So I don't know whether am I running out of time? Do I have time to? I think this is my second last slide, but if I'm out of time, then I can stop at this point.
Certainly have to wind up in 10 minutes.
Okay, no, then that's fine. I can, yep. I'll
but
I'll try to get through this quickly. This is literally my second last slide. So yep. Um, so so I've never talked about this before, what my personal opinions are. So this is my testing it out on the audience here, which I hope is a friendly audience. Why did I go in that direction? Why is that my preferred metaphysical direction? So I'd say, first of all, that I have an ontological conservatism in the sense that I want the average person's understanding of the everyday world to be, as far as possible, not fundamentally mistaken. Obviously, that's just a um, yeah, it's a temperament, if you like. Okay. But on the other hand, I would say that doesn't mean I'm conservative, because on a scientific front, I would say I'm a radical in the sense that I think that the theory we're looking for should say something constructive about the hard problem of consciousness. Um, so, right, because of A, I'm definitely not going to give up free choice, and I'm not going to give up absoluteness of observation by humans. Because of B, this is why I'm not really that anymore attracted to deterministic hidden variables theories like Bohmian mechanics, um, or ordinary spontaneous collapse models, because I don't see them. But it seems to me that the theorem, the local friendliness theorem, is that there is something interesting to say about consciousness, but then those theories don't say anything interesting about it. So what sort of theory would I like to be true, what I imagine could be true, would be some sort of subtle collapse theory, so which, like Penrose's ideas, is related to the emergence of space-time and to mental experience, but also one which, unlike Penrose's ideas, can be modeled by Born's rule. So is not going to produce anything which couldn't be simulated on a digital computer, in other words. Um, but yeah, so then my idea about thoughts or consciousness is that sensation only occurs when a multitude of possible mental states collapse to a single one. And so if my friend is on a reversible quantum computer, or any type of reversible computer, I should say, um, then I do not accept that my friend has the same types of impressions and sensations as I, because if it's reversible, then there is not this, irreversible collapse happening, which I think is, well, I speculate is essential for sensation. Okay, and then so this is literally my last slide, but it's really just a summary. So I might, I think I won't go through it. I'll leave it up and to leave a bit more time for questions. But just to say that, the takeaway is that I think that this thoughtful local friendliness theorem does have profound consequences for how we think about consciousness, and certainly has been influential on my own thoughts about the matter. Okay, thank you.
Well, thank you very much, Howard. A lot of content there, a lot to think about. Not too much time to discuss it. but I just wanted to throw in a couple of comments myself. Um, so the first time I heard anybody talking about a conscious quantum computer being interrogated, put in a superposition of mental states and interrogated, later and asked to remember earlier and so on, was a conversation I had on for the BBC Radio with David Deutsch in
Yes, yes,
1983.
yes.
Now, I don't remember anything about entanglements, which is the aspect which
No, no. So
induces
you're
that.
absolutely right. Yes, yes. And of course in the paper we talk a lot about what that yeah, David Deutsch's work in the early 1980s on this. So yes, you're absolutely right. Yes, he didn't have the extended Wigner friend of having entanglement, and he didn't have a theorem or anything like that. But the idea of yeah, exactly, having that this was a way of being able to have a friend who could be in a superposition was, yeah, I think definitely his. Absolutely. Yeah.
Right. And just to clarify my own mind, the idea of doing like an entanglement type experiment with the moon, so long enough that that a literal Alice and Bob could change their minds at the last moment and change the settings. Your point being that however much you automate something in the lab, uh, if replacing that by a real human being will tell you something about the nature of consciousness. Did I get that right?
I mean, I guess it's yeah, I guess it's I mean, obviously, if the experiment revealed, if we didn't manage to violate Bell inequalities in an experiment with conscious registration of the outcomes, that would tell us something extremely interesting and unexpected about consciousness. So yes, in that sense, it has a potential to tell us something about consciousness. I think almost everybody would say, well, that's not going to happen. We're going to get what we expect when we do an experiment like that. But it is, as I said, it was really I do think that's an interesting experiment. It's related to ideas that Adrian Kent has proposed about doing Bell theorems, doing Bell experiments with a yeah, he talks about the collapse locality loophole. So doing experiments with more rigorous ways of being sure that a an observation or an outcome has really happened. Um, But yes, but m most people don't expect anything interesting to happen there. And as I said, it's really just a way station. Whoops, sorry. So this one, yeah, this experiment, really just a way station to what I think are the really interesting experiments, which would be the ones involving a reversible friend.
Right. You have to have the reverse. We've got time only for a quick question by Barbara Temple. If we take Wigner's friend thought experiment seriously, is any quantum state ever properly collapsed, or can we only speak about quantum collapse relative to each individual observer? That sounds like the relative state. No,
Yeah, well,
it's
if we take Wigner's friend,
relational quantum mechanics. What I'm struggling.
yes. Well, I think the answer to that is that it completely depends on which uh interpretation of quantum mechanics do you have. I would say so that the local friendliness theorem, so a lot of people who work on these extended Wigner friend theorem will say that this is what they're showing, okay? That we should give up on the idea of absoluteness and it's all relational or whatever. And I do want to emphasize that no, they don't show that, right? There are several assumptions. Absoluteness of observations is only one, right? And so no, I would not say that they prove that. A lot of people take them to be more powerful evidence for that that's what we should give up. But it's not what the theorem says. You have a choice as to what you go up. And as I said, I'm not telling you which one you should give up.
Okay, well, it's a tradition of our thinking beyonds that we start on time and finish on time, and I think we have merely seconds to go. So it's just long enough for me to thank you very much, Howard, for giving us a lot to think about, and with a subject that's deeply fascinating but still deeply controversial. And a thank you also to our loyal audience. Don't forget us during the summer. Come back in a few months for more Thinking Beyond. And with that, I will say good night, at least in my time zone. And thank you once again, Howard.
Thank you, Paul. Then, yeah, thank you all.